Here's our two learning goals on 0.2. I can find the intercepts of a graph and the intersections of two graphs. We've actually done that with a calculator, but now we're going to do it without a calculator. And the second one is I can understand and can find the symmetry of graphs. If we talk about intercepts, right, x and y intercepts, if you just think for a second, if you're going to find an x-intercept, so think of all the points along the x-axis, and they all have something in common. And what they have in common is that the y-coordinate is always 0. If the y-coordinate wasn't 0, you'd be above the x-axis. If it was less than 0, it'd be below the x-axis. So to find an x-intercept, you have to find it when y is equal to 0. We kind of talked about that with finding the zeros in the last lesson. If you're on the y-axis, finding the y-intercept, all those points have something in common. And again, what they have in common is that the x-coordinate is always 0. So that kind of helps us understand, hopefully, how you find x and y intercepts. So if you're finding an x-intercept, it's where the point crosses or touches the x-axis. That's an important thing right now. It's not only crosses, but it's also touches. The y-coordinate is 0. So when you go to find the x-intercept, you let y equal 0 and solve for x. The y-intercept points where the graph touches or crosses the y-axis. In that case, you put 0 in for x, and then you solve for y. So let's do some examples. We want to find the x and the y-intercepts for y squared minus 3 equals x. By the way, this is not a function, and the way we can kind of tell is with that y squared. If I solve for y, I'll end up with a plus or minus, which means I'll have more than one y for every x. Anyway, that's beside the point. Let's find the x and the y-intercept. So to find the x-intercept, we put 0 in for y. So let's do that. I put 0 in for y. I end up with 0 minus 3 equals x. Well, that was easy. X equals negative 3, right? Now, when I write the answer, its an intercept is a point. So when I write it, it's going to be negative 3, 0. So you write it as a coordinate point. Okay, to go to find the y-intercept, now I put 0 in for x. So let's put 0 in for x. We end up with y squared minus 3 equals 0. I solve that, and now I have my y-intercept. So I'm going to add the 3 over. Y squared equals 3. Take the square root of both sides. Don't forget, again, square root of both sides means plus or minus. So plus or minus the square root of 3. Again, when you write your answer, it should be written as a point. So it's going to be x is 0. Y is the square root of 3. That's one x-intercept. The other one is x is 0 and y equals a negative square root of 3. So this one has one x-intercept and two y-intercept. This actually is a parabola turned on its side. And that's why it ends up crossing the y-axis twice. Okay, so finding x-intercepts, put 0 in for y, solve for x. Find the y-intercepts, plug 0 in for x, and solve for y. Symmetry. So we're going to talk about 3 types of symmetry. The first is it can be symmetric about the y-axis. So what that means, right, if I take an x and its opposite x, they both have the same y-coordinate. Like those are both the same. That's what makes it so it mirrors or reflects or has some symmetric across the y-axis. When it's symmetric about the x-axis, when I plug in opposites for y, the x stays the same, right? I do a positive y and negative y, the x will be the same both ways, so it's reflected or symmetric about the x-axis. When it's symmetric about the origin, both change. So the way you recognize this is you can see that piece. If you take this half, I'll outline it in blue. If you take it and reflect it across the x-axis up like that, and then across the y-axis, it should match up perfectly with that one. Another way to look at it is if you take the one side or one half of the graph and you rotate it 180 degrees around the origin, it's going to match up with that side too. That's how you can tell if it's symmetric about the origin. If I plug in x and negative x, I get opposites for the y. I get y and negative y. So graphs can be symmetric to other lines and points, but in this class, we're just going to focus on those 3. Being symmetric about the y-axis, the x-axis, and the origin. So here's how you actually test for it. To see if it's symmetric about the x-axis, this is like the formal test. It's a little harder to do. We'll do an informal one in a second. But I replace the x with negative x, and if you get the same thing back again, that means it's symmetric about the y-axis. A quick example of that would be y equals x squared. If I plug a negative x in for the x, I get y equals negative x squared. When I simplify that, it ends up being, right when I square the negative, it ends up being a positive. I get the same thing as I started with. So you get an equivalent equation. When that happens, it means it has to be symmetric about the y-axis. To see if it's symmetric about the x-axis, instead of plugging a negative x in, you plug a negative y in. So you take out the y and you plug in a negative y, and you see if you come up with the same equation. That one, here's an example. This is just a really simple example, but if I have x equals y squared, right, if I plug in a negative y, I get negative y squared. Well, when I square negative y, you still end up with a positive. You end up with the same thing as you started with. Hey, when it's symmetric about the origin, when you plug in a negative x, you should get the opposite back out. So here's an example, just a really simple one again. Y equals a negative x cubed, or y equals x cubed, excuse me, sorry. Y equals x cubed. If you plug a negative x in there, you end up with, when you cube a negative, it's just a negative. So I end up with a negative x cubed. That is the opposite of that. When that happens, it's symmetric about the origin. So that's the way you can do it formally, and it gets pretty tricky if you have a bigger equation, that are more complicated than those. There is an informal test, and that is, I can just take, if I want to see it symmetric about the y-axis, I just plug a number and its opposite in and see if I get the same y value. So I could plug in 5 and negative 5, or 1 and negative 1. If I get the same thing back out, that means it's symmetric about the y-axis. Now, you got to be careful with that. Technically, just because it works for one point doesn't mean it works for all the points on the graph. That's why it's an informal test. So this isn't a sure 100% of the time, but it's a good indicator. To check to see if it's symmetric about the x-axis, and you plug opposite numbers in for y. So you could plug 5 in for y and negative 5 in for y. If you get the same x value, then it's symmetric about the x-axis. If it's symmetric about the origin, you get opposites. So if I put in, say, 2 and get 5, if I put in negative 2, I should get negative 5. If I put in 1 and get 3, if I plug negative 1 in, I should get negative 3. So if that happens, it's symmetric about the origin. So the top three, if you do one of those three methods up here, the formal tests, it's a little more complicated, especially with bigger equations, because you have to do a lot of work to show that it's an equivalent equation or that it's the opposite. It's a lot easier just to plug numbers in. So a lot of times we'll do this informal test just if we want to check really quick to see what we think it is. So here's some examples. Let's do this. It says find the type and symmetry of the graph. So let's start with this number 2 up here. Let's check to see if it's symmetric about the y-axis or the origin. So the way I check for that is I just plug in a negative x. And what I'm checking for is, do I end up with the same equation back again, or do I end up with the opposite? If it's the same, it's symmetric about the y-axis. If it's the opposite, it's symmetric about the origin. If it's neither, then it's none of the above. So let's go ahead and check that. I'm going to go y equals. If I cube a negative, it just becomes a negative. So it'd be negative 2x cubed. I have minus a negative. That changes to a plus. If I look at this and this, they are opposites of each other. So that it's not symmetric about the y-axis. That means it has to be symmetric about the x-axis. Look at number 3. Let's check that one. Let's do the informal test this time. So I want to plug in opposites for x. So let's plug in, let's plug in 3 for x. Then we'll also plug negative 3 in for x and see what happens. So if I plug 3 in, the absolute value of 3 is 3. 3 minus 2 is 1. If I plug in a negative 3, the absolute value of negative 3 is 3. 3 minus 2 is 1. So I plugged in opposite numbers and I got the same thing back out. That means it's symmetric about the y-axis. And if you forget, just think about where those points are. I've got 3, 1, and I got negative 3, 1. Well, you can see that it's symmetric about that y-axis. Now again, that's informal. It doesn't guarantee that's going to happen, but I mean, you can try it with some more points and you'll see that that relationship keeps happening. Okay, so let's check number 4. The only time it's going to be symmetric about the x-axis is if it's not a function. And so look at the y. If there's a y squared, or in this case, the absolute value of y, that's a pretty good indicator that if it's going to be symmetric, it's going to be symmetric about the x-axis. So let's check. Let's plug opposites in for y. So if I plug in, let's do 2 for y. That means I also want to plug in -2. I want to see if I get the same thing, the same x back out. So if I plug in 2, I get for y, I get the absolute value of 2 equals x minus 2. Well, the absolute value of 2 is 2. I can add that 2 over, so I get a positive 4. Try a -2. The absolute value of -2 equals x minus 2. Hey, well, that still comes out to be 2. I add the 2 over, and I end up with 4. So when I plugged in opposite for the y's, I ended up with the same x. I ended up being 4 both times. So that's doing the informal test, but that indicates, or it's probably symmetric about the x-axis. But again, you only have to worry about that. If it's ever in the y equals form, it will not be symmetric about the x-axis. It will only be either the y or the origin. The only time, and think about what that looks like. If I graph those points, 2 and -2, right? It's not a function. So if it's symmetric about the x-axis, it can't be a function. So that means, again, you're looking for when something's happening to the y, whether it's absolute values or whether it's a square. All right, let's look at these next definitions of even and odd. This is pretty easy because it goes along with symmetry. So a function is even if I plug in opposites, -x and x, and they're equal. You get the same thing back out. So what that really means is if it's even, it's symmetric about the y-axis. So if you check and it's symmetric about the y-axis, it also means it's what we call an even function. Look at some examples up here. We have y equals x squared, y equals x to the 4th, y equals x squared plus 3, y equals x to the 4th plus x squared. There's a reason why they call it even. If you look at all the powers up here, a square is an even power, 4th is an even power. This is a squared, 3 has a 0 power. This is a 4th, this is a square. So they all have even powers. So what happens, let's use this last one for an example. When I plug in a -x, so what's going to happen is that even power is going to make that -x a positive x to the 4. So I get the same thing. And the -x squared will be a positive. So when you plug in a negative, it switches it back to a positive, which means you get the same thing back out. But again, the big thing is that if it's even, it's symmetric about the y-axis. So if you want to check to see if it's even, you check the same way as we check for symmetry on the y-axis. If a function is odd, you get opposites back out. So if I plug in a -x and x, see how they're opposites of each other? So that's how you check. Well, that's really what we said. That's how you test to see if it's symmetric about the origin. So odd functions are symmetric about the origin. So you test them the same way. You plug in opposites. The reason why they call it an odd, here's some examples. Notice how it's x to the 1st power. It's x to the 3rd power, x to the 5th power. Over here I have x to the 5th minus x to the 3rd. The reason why that works is because if I plug in a -x, if it's an odd power, it flips the sign. So a -x to the 5th power is a -x to the 5th. Sorry, that's supposed to be a negative. A -x to the 3rd power is a -x to the 3rd. That changes to a plus. So if you look at that, that is the opposite of that. So if you have an odd power, it will flip and become the opposite. If you have even powers, it will stay the same. So that's where the name comes from, if a function is even or a function is odd. Now, just to be clear, it's possible that a function is neither. Sometimes it's even, sometimes it's odd, but it could be none of the above. So let's go through and do these. We're going to check and see if they're even or odd. So just think about what happens. We're going to plug in a -x and see what I get back out. So if I do f of -x, if I plug a -x in there, so I end up with a -x to the 3rd power. That'd just be a -x to the 3rd. Minus a -x would be a plus x. So if I look at that, that is the opposite of that. That means it's symmetric about the origin, so it means it's an odd function. Let's try this one. Plug in a negative. I'd get a -x to the 2nd power minus 4. Well, the negative x to the second power makes it a positive x. Whoops, I don't need those parentheses anymore. So that would become x squared, and it's still a minus 4. Hey, that's the exact same thing as I have there. So when I plugged in a negative x, I got the same thing back out. That means it's symmetric about the y-axis or an even function. Okay, check number 7. If I plug in a negative x, I'd get a negative x squared plus 2 times negative x plus 2. Okay, so start with the negative x squared. That makes it a positive x squared, 2 times a negative x, and a plus 2. So if you look at it, this is not the opposite of that. It also didn't stay the same. Like the x squared stay the same, the 2x changed signs. So this one is an example of one that's neither. Okay, it's not even, it's not odd. Hey, last thing is points of intersections. There's 2 ways to find a points of intersection. One is through substitution, where you solve one of them for x or y, and then you plug it into the other equation. The other one is you can solve them both for either x or y, and then you just set them equal to each other. So you're essentially doing the same thing. Now again, we did this with the calculator, right? We graphed them and found points of intersection. So this is doing it algebraically. So let's do this the first way. I'm going to solve for, if I solve for x in this equation, I'll have to plug it into the square, which sounds like more work for me. So I'm going to solve for y right here in this equation. So I'm going to minus the x over. I get negative y equals 1 minus x. Divide by negative 1, y equals negative 1 plus x. That's what y is equal to. Okay, now I take that, and I substitute it in for a y right there. So I end up with x squared minus negative 1 plus x equals 3. I'm going to distribute that negative through. I get x squared plus 1 minus x equals 3. This is a quadratic equation, so I'm going to get everything on one side and factor it. So I'm going to go x squared. I'm going to slide that minus x over. I'm going to minus the 3 over with the 1, so minus 2 equals 0. Now I'm going to factor that. So 2 sets of parentheses, x and x. The factors of negative 2 that add up to be a negative 1 right there. That would be minus 2 and plus 1. This one then would give me a x equals 2. This one would give me x equals negative 1. Now, this is where you have to be careful. Those are the x values. The question is asking for the points of intersection. So I need to take that and plug those x's back into one of those 2 equations over there. So I'm going to go 2, plug it in for x, find the y, negative 1. Plug it in for x and find the y. So if I plug 2 in right here, I get, that was not the right equation. Let's plug it in right here. So if I plug 2 in there, I get negative 1 plus 2, which is 1. If I plug negative 1 in there, I get negative 1 plus negative 1. Okay. There are my points of intersection. So that was method number 1. You solve one of the equations for x or y, and then you plug it into the other equation. Method 2 is to solve for both equations for the same variable. Let me just show you how you'd set that up. So we already solved this one for y. This one was, now I already forgot, what was it, negative 1 plus x. If I solve this one for y, I'd move the x squared over. Negative y equals 3 minus x squared. Divide by negative 1. So I get them both in the y equals form. And now I just take what they're equal to, that, and I set them equal. Negative 1 plus x equals negative 3 plus x squared. That's going to be in that same equation I just solved, so we go through the steps of solving it. So you can do it either way. Solve for one and substitute it in, or you can solve for both and set them equal to each other. That's it. So the main concepts here is you should be able to check for symmetry. And along with symmetry, just know that if it's symmetric about the y-axis, it's even. Symmetric about the origin, it's odd. It can also be symmetric about the x-axis if it's not a function. So be able to test for all 3 of those, and then be able to find points of intersections find intercepts also, x and y intercepts and points of intersection without using the calculator. And that's all I have for you. Thanks, guys.